So this is the question that we'll be discussing in this video. An open tank is to be constructed in the shape of a cuboid with volume 4 cubic meters. The base and sides are to be made out of thin metal sheets. Find the dimensions of the tank such that the least possible amount of sheet is used. You're welcome to pause the video here and work it in your own time, but I'll just move on to the solution. So if we interpret the question and put it into a diagram, well, it's pretty much a cuboid, and I'll just label the sides as X, Y, and W, and the top is open. That will be relevant in the coming steps. So we identify this as an optimization problem because it's asking for the case where least possible amount of sheet is used. So we have to minimize the surface area pretty much. So it's an optimization problem, and initially it might seem like there are 3 independent variables. However, it turns out that's not the case. It'll be evident in the coming steps. So let's just translate some of this information to the relevant mathematics. So the volume of the cube is x times y times w, and we are told it has to be 4. So we have this equation here, and then the area of material, importantly, it's only the base and sides. The top is it's an open top container. So this shaded region here is open. So the area of material will pretty much be the surface area of the cuboid, except the top part will not be in there. So that's why there's only one set of XWs, there's 2 sets of XYs, and then 2 sets of YWs. So using these 2 equations, we can actually eliminate one of the dimensional variables. We know that XYW has to be 4. Rearranging that for W, we see that W is basically 4 on XY. So this is important because now W is no longer an independent variable. It simply depends on XY. So that'll actually boil down the dimensionality of our problem, and that's pretty much a consequence of having a predefined volume. So we can substitute this into the area equation, this value for W. We substitute it into this equation here, and we have it right here. And then after substitution, we get this equation here for the area of material used, area of thin metal sheets used. So then we have this function. It is the area of material. It's in terms of the 2 variables x and y, and this is the function here, 4 on y plus 2xy plus 8 on x. So this is the function that we need to minimize. So now it's evident it's actually a 2 variable optimization problem rather than 3. And then we can do this in a couple ways. We'll first discuss using partial derivatives. So I've just included this in a slightly different index notation because it'll be relevant. It'll be relevant when we are using calculus. It'll be more useful to have it in this form, but it's pretty much the same thing. This is the function that we need to minimize. So the first way is we are gonna just use calculus, and then we are gonna get to the answer. What we need is simply the minimum possible surface area. So we'll use calculus to simply get to the answer, but then later we'll try to tackle this problem by graphing the surface, because in fact this wouldn't be a single line graph because there are two independent variables. It's a two variable optimization problem, so we'll have to sketch a surface in a 3D plot. We'll consider that later. First, we're just going to use calculus to skip all the steps and then arrive at the answer that we are looking for. So there are two variables in this function. So the first thing is, since there are two variables, we can't really take full derivatives, and that's where this idea of partial derivatives come in. It'll be evident why we are calculating these particular partial derivatives of interest later. Actually, all of these will be relevant. We are actually calculating all the first and second order partial derivatives. There isn't just one of them, as in for full derivatives, of course, there's just one first order derivative and one second derivative. But for partial derivatives, there are more options, and we'll get to that shortly. Why we are calculating these will be evident in the next few steps, but first let's just calculate all the first and second order partial derivatives for this function. So how exactly do we differentiate something when there are two distinct variables, two distinct independent variables? Well, firstly, we can do it in two ways. We can do it with respect to each variable. So if we take it with respect to x, the partial derivative of a with respect to x, del a del x, we will assume that y is then not a variable. We'll assume y to simply be a constant. And when we are taking the partial derivative with respect to y, we'll simply consider y to be the variable and x to just be a constant. So back to here, working on the partial derivative with respect to x, del a del x. So first, it's rather than this section, I'll use this equation because this form is much easier to differentiate. So for y to the power of -1, it's simply all a constant because we are assuming y to be a constant, so the derivative of a constant is 0, so that's why we have 0 right here. And then 2xy, again 2y is just a constant, so we can have that in front. And differentiating x with respect to x, that's just 1, so the only thing remaining is the constant, which is 2y, so we have 2y here. And then finally 8x to the power -1, differentiating that is pretty straightforward. You don't really need to even know anything about partial derivatives for that part, so it's just 8x to the power -2, and then this is pretty much 2y minus 8 on x squared. And then on the other hand, in this case we are going to consider y to be the variable and x to simply be a constant. So in this case we just differentiate 4y minus 1, 4y to the power of -1, and we get this. That's pretty straightforward. And then 2xy, we assume x to just be a constant and then y to be the variable. So 2x is just a constant, so it's in front, and then y, the derivative of y with respect to y is 1, so we can forget that. And then again 8x minus 1, that's just a constant because x is a constant, so it's the derivative of a constant is 0, so we have 0. So this is pretty much what we get when we partially differentiate with respect to y. And then there's the second order partial derivatives. The most obvious ones are this one and this one. So again, we are doing exactly the same thing. We're just gonna again partially differentiate it with respect to x, and this one with respect to y. We're just doing the exact same thing we did as before, just like for full derivatives. We're gonna we are gonna ignore y. We are gonna just assume y is a constant, and then differentiate with respect to x. So we are working with this now. We're going to differentiate this, and then 2y, that's just a constant, so it becomes 0, so it's just 0. But this thing can this thing won't be a constant. Minus 8 on x squared. If we differentiate that with respect to x, we get this thing here, and this is the same thing. So 16 on x cubed, that's the second order partial derivative with respect to x. And then the exact same thing here, 2x, if we differentiate with respect to y, 2x is pretty much 0, so that's 0. And then minus 4 on y squared, that's this here, so we get that. It might seem that these are the only two possible second order partial derivatives, but that's not exactly the case, because we can have these things, the so-called mixed partial derivatives. So this is the case where first we differentiate, we take the partial derivative with respect to x, and then the next time around we differentiate it with respect to y. And we can also do it the other way around, first with respect to y and then with respect to x. So it turns out it's an important relationship that these two will be the same. You can try that out. So let's just try, let's just differentiate this with respect to y, so that we get this, thing right here. So 2y minus 8 on x squared. So now we're differentiating it with respect to y. And when we do that, for 2y, we're just going to get 2, because the derivative of y with respect to y is just 2. And then the other thing is just a constant, because now we're taking that to be a constant. We are taking x to be a constant, so that's just 0. So 2 minus 0, it's just going to be 0. And the other way around, where now we're differentiating del a del y with respect to x to create the other mixed partial derivative. And then it turns out, well, 2x, if we differentiate that with respect to x, it's just going to give us 2. And then this whole thing is again a constant, so it's 0. So 2 minus 0, 2 minus 0, so both these things are in fact 0, and they are in fact equal. And that's an important relationship, and we'll need, so we have now calculated all the first and second order partial derivatives possible for this function. And we are going to need all these derivatives in the coming steps to actually solve the problem at hand. So, well, this is an optimization problem, so the most obvious thing to do is to find the stationary points for the function for this function, so that we can then determine the minimum. So the rule with stationary points for a function of two variables is that both the first order partial derivatives must be 0 at the same time. You might create an analogy with full derivatives, where it's pretty much we want the derivative of something to be 0 for it to be classified as a stationary point. Let's say in a graph like this. So this would be a stationary point. So we just need the derivative to be 0, the full derivative. But we are dealing with partial derivatives here. So in this case, we have two derivatives with respect to each variable, two partial derivatives, and we require that both these are 0 at the same time, simultaneously. So simply substituting the derivatives we found before, we come here. So we have these two equations, and importantly, these must be solved simultaneously to get the stationary point, because that's pretty much the rule we have. Both of these must be true at the same time. So we're gonna use, to solve this set of simultaneous equations, we're gonna use substitution. So we're just gonna rearrange one of the equations to make this, and then we're gonna substitute that thing here, this x here. It's an x squared here, so we substitute the exact same thing in the other equation, and then a little bit of algebra, and we're factorizing out y. So we have y, let me just write that out, y 1 minus y cubed equal to 0. So that's what we have, and then from the null factorial, obviously, at least one of these should be 0. This should be 0, or this should be 0 for this to be true. So we have the first solution, y equals 0. So this is a solution. This is a solution for this particular function, but it's physically meaningless for our problem. Why is that? Well, if it has a 0 dimension, that pretty much means the actual tank we are constructing doesn't exist. So it's not meaningful for our problem, so we simply reject this outcome. Also, if you think about it this way, if you substitute this in this equation, it's gonna produce a result where x tends to x tends to infinity, or you might as well say x tends to yeah, pretty much x would tend to an infinitely large value. So so the result is it wouldn't be a well-defined extreme, simply because it tends to an infinitely large value, and also, well, if y, so pretty much this result makes sense, because if y is 0, well, the other dimension, one of the other dimensions has to be very large in order to have the volume of 4. But really, it's not important for us, because it's not physically meaningless to have a zero dimension. So it's not what we're interested in. This other branch of the solution, 1 minus y cubed is equal to 0, so y cubed is equal to 1, and then y cubed equal to 1, so y is equal to the cubic root of 1. Importantly, it's just going to be y equal 1. Importantly, there's no plus or minus issues here, because it's a cubic root, and the cubic root of 1 is indeed 1. So then we substitute this in our initial equation, the one right here. We don't have this infinity case now. We substitute y equal 1 in there, so we get x is equal to 2. So we have our solution for this set of simultaneous equations. That pretty much means the only stationary point of value for us of the function axy occurs when x equals 2 and y equals 1. Again, also it's important, if we're thinking about the actual point, it will be where x equals 1, y equals 1, and then the function, the area will be whatever the area is at that point. So that's the actual turning points. We need all these three things to define the actual point in the coordinate system, because it's a 3D plot. But the stationary point occurs when the independent variables are these two. So this is pretty much where it occurs, but the actual point, we need all these three pieces of information to identify that. Of course, this has a value, this has some value. We will investigate what the value is later, the actual area, the numerical value of the area. But the idea is it pretty much occurs at this point, x equal 2 and y equal 1. So that's a stationary point. We have a stationary point, but what we are asked for in the question is pretty much a point where the value is a minimum, where the area is a minimum. So there are three principal types of stationary points in a 3D plot. It's these three. It's somewhat analogous to the one variable, one independent variable graphs. There's a relative maximum, and then there's a relative minimum, and also there's the so-called stationary points of inflection. The maximum and the minimum, so this is pretty much exactly the same thing, but instead in 3 dimensions. So it's a surface plot. The surface looks like a maximum in all directions, so however you look at it, it's a maximum. So this is analogous to this case in 2D, and then the relative minimum is also pretty much the same as this, but again with respect to both variables, it's a minimum. It quite literally looks like a bowl or something like that. But this other thing, the saddle point, is actually a much more important, as in a little different. It's not really a 3D version of an inflection point. Sorry about that. It's not really a 3-dimensional version of an inflection point. Actually, all stationary points of inflection, in 3D plots are saddle points. However, it doesn't really work the other way around. All saddle points aren't stationary points of inflection. It's actually a general term, and stationary points of inflection in the 3D space is also one example of the saddle points. So in general, what a saddle point is, if you look at it from one direction, it looks like there's a maximum, but in the other direction, as in if we look at it from a direction that's 90 degrees or orthogonal to this, it looks like a minimum. So it's pretty much it's a stationary point. So the first order partial derivatives are 0, so pretty much del A, del X, and del A, del Y are still 0. That's still the case, but we can't really classify that as meaningfully classify that as a maximum or a minimum, because with respect to one variable, it's a maximum. That's why if you look at it from one direction, it's a maximum, but from the other direction, it's a minimum, as in with respect to the other variable, it's a minimum. So that's, in general, that's what we call a saddle point. There are different types of saddle points, but in general, that's the case. So that's why it actually looks like a saddle on horse. If you look at it from one direction, it's a maximum, but in the other direction, at a 90-degree angle, it'll be a minimum. You can look up what a saddle point looks like online. So it pretty much looks like one of the saddle points could simply look like a saddle. So that's where the name comes from. But you can just look up different types of saddle points, illustrations of the surfaces, but I won't go into detail because that's not really the point of this video. We are trying to discuss a relative minimum, a practical example of a relative minimum. So that's all with that. Also, another bit of theory. There's a test for full derivatives. We simply just to find whether it's a maximum or a minimum, we just use the second derivative. So the sign of the second derivative or the concavity will tell us whether it's a relative maximum or a minimum. But for partial derivatives, for surfaces actually, for surfaces, it's a little bit more, it's a little bit different, because it's not just finding the second order derivatives. We have this test. We evaluate the quantity called the Hessian, or the H for the Hessian. We evaluate it at the point of interest, and if so this is how we find the Hessian. This is pretty much what the Hessian is defined as. So you can see this is why we evaluated the second order derivatives before. We are going to need both those and also the mixed derivative, but again, the mixed derivative is the same which order you take it as, whether it's del x del y or del y del x. So it's pretty much the same if you take it this way around. So this is the quantity of the Hessian. If we evaluate it at the point of interest, at the stationary point we are considering, this is quite important, at the point, if the value of it is greater than 0, and also the value of this partial derivative, again at that point, this one at that point is less than 0, then it's a relative maximum. Again, if the Hessian is still greater than 0, but this derivative is greater than 0, then it's a relative minimum. And then in the case where the Hessian is less than 0, it would be a saddle point like we discussed before, but we wouldn't really get, we won't get, in fact, if the point is a saddle point, it wouldn't really be the answer to our question, because we're asking for a minimum, so we want it to be this case, but we need to investigate and see if the stationary point we found does fall into this case. So those are the three cases. Well, of course, there's also the case where H is 0. So in this case, we really can't decide. The test is inconclusive. So we are gonna have to look at it. Either we could graph it and see what exactly the case is. But generally, these three cases are sufficient to tackle these problems. So now we are going to use this test and distinguish what our stationary point at x equal to y equal 1 is. So the Hessian for the generic point. So now we haven't yet substituted the point of interest, the coordinates of the point of interest, these coordinates. We're just working with the general formula. So this is the formula for the Hessian, and then we are just gonna substitute the value of this derivative, and this derivative that we previously found, the general case for the whole function. So we have it right here. So pretty much this is substituting it in for the formula and then simplifying it slightly, not too much, because we will have another simplification here, so I'm just not going to multiply these things, these two. Pretty much something like this is what we're going to get. And now we are going to find it at the point of interest, meaning we are going to substitute this actual point into this equation so that we can get a numerical value for that particular stationary point. So x equal 2 and y equal 1, and so the Hessian at the point 2, 1, where the independent variables are 2 and 1, and the value turns out to be 12, and 12 is clearly greater than 0. So that pretty much means it's either case A or case B. If you remember properly, the cases A and B will be different depending on the value of a certain derivative. Like for both case and case B, the Hessian will be greater than 0, but it depends on a particular derivative. And so again, we have the Hessian is greater than 0, so that's all right. But then we also need to find this particular derivative at this point. Again, not just the derivative for the function, we need to substitute these values. So this is pretty much the notation is saying this derivative, but substitute x equal 2 and y equal 1. And then if we do that, we have already found this derivative previously, and then if we substitute these values, we get this. So and the answer is 2. The numerical value for this is 2, and then it's greater than 1. It's greater than 0. So using this piece of information and this piece of information, we conclude that this is the case. It's the case B of the test. So the stationary point is in fact as we needed. It's a minimum, and so x equal 2 and y equal 1 will give the minimum area, because it's a relative minimum of the function. And again, a little bit of just before making a conclusion, we are going to need a little bit more details. We know that this is the volume must be 4, and the volume is x times y times w. We use x and y because we eliminated w earlier, so we just determined 2 of the dimensions, and we'll just use this equation again to find what actually the value of w is, since w really depends on those 2 previous dimensions. And it turns out that w is 2. So now we know all the dimensions x, y, and w. X and y we found with calculus, and w we simply just substituted it, and knowing that it's dependent of x and y. And then this would give the area. Again, just as an extra step, we are going to find the actual minimum area, the value of the area, how much sheet material will be required. We're going to use the equation that we introduced before, that we just translated from the question statement, since it's an open top container, so just 1 of these, and then 2 of this and 2 of this. So pretty much if you solve that, it turns out that the area will be 12. Obviously we need units for that. We are going to add that in the next slide. So the conclusion: the dimensions x equal 2 meters, y equal 1 meter, and w equal 2 meter will produce a tank with the least possible area of material. And that's pretty much what the question is asking. But as an extra step, we are just going to say, in this case, the actual area of the thin metal sheet will be 12 square meters. That's pretty much what the question is asking for. We used calculus for this to get to the final answer, to find that critical point we need. But then we might as well just analyze the graph, and by doing that, again, we can visually see what the point is, and to see if it's actually the minimum possible point. Well, mainly for illustrative purposes, but we could also just use it to get the answer in the first place. So we can't really, I guess you could sketch, like a this would be a 2D graph, but in this case we are gonna get a three-dimensional graph. You could try to sketch it, but I'd say it's going to be a fruitless attempt in 3 dimensions. So instead, we are just going to do that computationally, because it makes more sense to do that computationally. It's more of a job for a computer than to just sketch a 3D graph by hand. In fact, this is quite important because not always do we have this privilege of getting an analytical answer using calculus. There are, let's say, if in fluid dynamics or something like that, there's many cases where we really can't seem to get an analytical solution, or a solution with calculus is too difficult. In those cases, we can just solve them numerically, as in graph them, and then find the values for that. But then again, doing that by hand, it doesn't seem like a fruitful attempt. That type of a job is best suited for a computer, doing a lot of things, but doing a lot of things that are pretty much exactly the same. So hence we are going to sketch this. We're going to sketch this graph computationally and see if it agrees with the answer we got using calculus. Because not always do we have this option to use calculus, but we can analyze the graph computationally. So we're gonna, in this case, since we have both options, we're just gonna sketch the graph and see if it's gonna give the same results. So this is the function that we need to graph in a 3D plot. I'm going to use MATLAB for this to make this sketch. So this is the code that has to be implemented to sketch this particular graph. What I'm doing here, first, almost as if taking x and y as linearly independent vectors, I'm defining a Cartesian plane, in this case called a mesh grid, from 0 to 5 with steps of 0.1. So this is pretty much the plane to which the function will be, the function a will be implemented. So why from 0 to 5? Well, in theory, the graph should exist, should go to infinity, but we can't really do that. We can't realistically do that, and of course, since we can't do that, a computer can't as well, because it has to have some finite value where it stops. Well, you can have it to a very, very large value, let's say 100,000 or something, 100,000 or something, but in this case 0 to 5 is more than enough to make a conclusion, because it seems like from 5 it's just going to have the exact same trend. But yeah, it just has to be finite. And again, what's this step? Well, again, in theory, the real plane has infinitely many points, right? Because between every two numbers there's a third number. So for that to be true, we'll need infinitely many points. But again, we can't do that realistically, and so can't a computer. So we're just going to discretize from 0 to 5. We are going to discretize the domain and have discrete points, and that's with steps of 0.1. Again, it's just to make sure that it'll make sure that the points, the number of points are finite, because if it's infinite, then again it can't really be processed by a computer. So you can use a much smaller discretization step, like let's say 0.00001 or something, but that again comes at a computational cost. The higher the precision, the higher the computational cost. But this, again, I might as well run a high precision discretization step, but 0.1 is more than enough for this particular question. If you understand after this graph, but it's possible to go for better precision, but it's not necessary in this case. it just has to be finite. It can't just be 0. So that's just the thing here. That's why we have this discretization step and these intervals, just to make sure that these are finite. And that's step 1 of the code. And then in step 2, I'm just implementing this exact same function given here, but in a notation that the computer can understand, in MATLAB notation. So that's pretty much it, pretty much implemented that. An important thing is these dots. These are before every operation, I'm using these to ensure that the computer knows these are meant to be executed as element-wise operations and not matrix operations. Without the dot, it'll think it's a matrix operation, but that's not what we need here, just element-wise operation. That's the point of these dots. So yeah, that's pretty much implementing the function A using the correct notation used in this particular coding language. And then this surf, what this is going to do is simply it's going to sketch a 3D plot, x and y, taking x and y as the 2 independent variables which we used to define a Cartesian plane before, right here. And then it's going to plot it with the function a, which depends on this 2 variables. So that's pretty much, this is pretty much the step where the 3D plot is made. And then these labels are just for pedagogical reasons, but really it's not necessary. So I'll move on to the graph so that we can see if it agrees with the calculus we used before. So here we have the result of running that particular code. So this is pretty much the graph of the function A, area of material, that depends on x and y, which are 2 of the dimensions of the proposed cuboid shaped tank. So if you take a look at this, it does appear that the minimum of area occurs in somewhere like around here, in some minimum point, and of course particularly in this direction the area will increase rapidly, and then again pretty much in every direction the area is going to increase. So let's take a look and see if we can spot the minimum area in the graph. We already knew that it had to be y equal 1 and x equal 2. So this is in the YA plane, or you might say the YZ plane, or pretty much y and the area of material. And in this plane you can see this minimum should be occurring at some point where y is 1. From the graph you can pretty much see that the minimum is somewhere around here when y equal 1, but we still don't know x because we are weaving in the YA plane. And if we turn it around and then look at it directly from the XA plane, let me just align this properly. Yep, that's it. And then if you look at it from this angle, again it turns out it appears that the minimum is somewhere, it's closest to 2, you know, when compared with 2.5 and 1.5, it definitely is closer to 2. So yes, indeed, x equal 2, y equal 1 seems like the point that produces the minimum value for the dependent variable or the area. Again, we can also check, well, well, the good thing with doing this computationally is that we now have all the values of area for all these discretized points we have. So let's say at this point the value of area is 18, at this point 12, like that. So if we just turn it around in this xy plane, let's see, let me just align it. Yep. So if you turn it around like this, now we are really not seeing the heights because it's turned around in this plane. We can just scroll over points and then see what the respective areas are, because all these have been quite straightforwardly calculated computationally, the numerical value for each of these points. So let's just see x equals 2. X equal 2 is this line, and then y equals 1, which is pretty much right here. So 12. So this has to 12 is indeed what the area we got from the calculation as the minimum area. So this has to be the minimum. Let's just check around it. Well, 12.1, 12.4, 12.8, clearly larger, 13 becoming larger and larger, 13.9, 29 very much larger, so definitely not very efficient, 23, 16 again not as bad but not relatively larger than 12, 14 it's becoming closer to 12 in this region, and then in this sense really bad, 43 or 42, really inefficient. So 12 cubic 12 square centimeters, because we are talking about the area. So this is indeed the minimum. So if I just turn it around, yes indeed that looks like the minimum. And that's pretty much how we would do that by graphing the surface. Again, it would have been possible to graph it by hand, but then it would be somewhat pointless to do a scale diagram, particularly with three dimensions involved. It would be kind of fruitless to do it by hand, because that job is more suited for a computer, because again it's pretty much doing the exact same thing multiple times. That's how you would sketch a scale graph. So this was consistent with what we got, the final answer we got using calculus, and that's really nice, because again, that for that method we didn't need to do like extreme numerical calculations. We didn't need to construct a scale diagram. We didn't need computational power. We were able to do that using calculus, just using pretty much logic and the idea of calculus, the idea of multivariable calculus to be particularly in this case. So it's nice to have a consistent answer from that method, and again graphing this, which was done computationally. So yeah, this is pretty much again we can extend this this graph in different directions as long as it's finite. It can't be infinitely large. It has to be finite, because again it's being actually sketched by the computer. It can't really process an infinitely large amount of data. It can be very large, but it has to be finite. And then again, as I mentioned before, it's done by pretty much discretizing this whole thing, the whole surface, and then calculating the values at those discrete points. So if we had the discretization step of 0.1, if the discretization step is smaller, then these boxes would be less visible, meaning the curve will be smoother and smoother. So you can see a bit of at these points it looks a bit it looks like it's not like a curve, it's more of straight lines, a bunch of straight lines, but that will look more like a smoother curve by increasing the discretization step. So pretty much increasing the precision, having a step smaller than 0.1, but then again it can't be 0 because that would produce an infinite number of points. The computer can process a very large number of points, but not an infinite number, because that doesn't seem realistic. So here we can make it smoother by increasing the discretization step, again by decreasing by decreasing the discretization step. We are making it smoother by increasing it, as in making it less precise. We can make this look even more straight line-ish and less of the curves. That's pretty much, I guess, we could play around with the sketch like that. But generally this is the curve of the area, and we get an answer that agrees with calculus using computationally graphing it. And again, the importance is that sometimes we cannot solve we can't get an analytical solution using calculus, so we have to resort to computational power, like in this case. An example I gave before is in the field of fluid dynamics. That could possibly happen there in fluid dynamics, but that's pretty much the case. So we found the answer to the previously given problem in two different methods, using calculus and computationally, and the answer was consistent. And I guess in a way this question was sort of to give an idea of the importance of calculus and a bit of an insight to partial derivatives and multivariable calculus, and then also this bit of computational sketching the surface computation. That's it. Thank you.